Hi, everyone. Welcome back. So we continue the second part of this talk. We continue the proof of our main theorem in the first part. But before we begin the proof, let's first of all quickly review the whole statement. The main theorem says, if we have a singular curve C with degree D and genus G, H double point, one cuspidal singular point Z, then for any K range from 1 to etc. to D minus 2, we have the following two inequalities. So just a brief recall, like this cuspidal singular point Z will give us a link of singularity. And actually, this is an algebraic knot. Okay. And R is not invariant. You can basically regard this as the V function up to some gradient shift, sorry. But in order to prove this, actually, we're going to a more general picture for the singular curve. The picture is like, now C, we just regard it as a reduced curve of genus G. Now we don't assume it only has one singular point. We assume like it has the singular point Z1, Z2, etc., Zn. And each singular point, it could be cuspidal or it could be non-cuspidal, meaning like we don't know whether the link of the singularity is a knot or a link, and we don't know how many components it has. And we let the corresponding link of the singularities to be L1, L2, etc., Ln. Sorry, let me change the notation here to be M to make consistent. Each singular point Zn will give you the link of singularities Ln, and we don't know whether this is a knot or a link. And we let R1, R2, etc., Rn to denote the number of the components of Li. So our abstractions in our main theorem comes from the D invariant in Heegaard Floer homology package. Let's first of all briefly review the definition for the D invariant and the themes we need to use extract from the Heegaard Floer homology. So the D invariant actually is a three-manifold invariant. It is a rational number, and originally it was defined by Oshva and Zabel for rational homology spheres Y with a spin C structure S. It basically records the gradient information about the Heegaard Floer homology HF minors of the three manifold Y with the spin C structure S. So just to make the picture more clear, so we have the rational homology sphere Y, and we give a spin C structure S here. And then by the work of Oshva and Zabel, then one can associate a chain complex CF minors of Y and S. So this is not a three-manifold invariant yet. However, when we take the homology for this chain complex, we get a three-manifold invariant. And this is not only a homology, but you can regard this as a module over Fu, where this F is the field Z over 2Z. And you can just regard it as a formal variable. Keep track of the base point in the Heegaard diagram. So the key theme is like once Y is a rational homology sphere and you fix the spin C structure then you always get the structure of the module HF minors of Y at the spin C structure S. It's written as one free part as Fu plus some U torsion part. So the gradient information for this U is -2 each time. The homological gradient of U is -2. So you have the generator for this Fu tower. Let me call the generator as A. Then the next one is UA because U acts on this tower gradually. And you have U square A, etc. Once you know the gradient for A, for example, if you know the gradient is 0, then UA has the gradient -2, -4, etc. So the key point for the gradient information in the tower part is the generator. And that's actually how we define the D invariant. So we basically record the D invariant of Y at the spin C structure S as the gradient of the generator of this Fu part, free part. So there's a very So this kind of invariant is very useful when we study full manifolds. For example, if we know like our Y is a rational homology sphere, bounds a rational homology ball X, then there is a strong restrictions for this D invariant of this boundary Y. We should have the D invariant of Y at the spin C structure S equals to 0 for all spin C structure X over Y that can extend to the rational homology ball X. This is given by Oshman-Zabel. So in order to study which full manifold can be bounded by some rational three manifolds, one thing we can study is using the obstructions from the D invariant. But this is still very restrictive here. Later, this D invariant can be generalized to other three manifolds with positive first Betty number. There are other versions of the generalizations when we consider the first Betty number of the three manifold is greater than 0, meaning like now our Y is not a rational homology sphere. And also there are some generalizations when the full manifold it bounds is not a rational homology ball, but it's just some arbitrary full manifold with positive second Betty number. So there are some generalizations for this result, but most of the generalization restrict our full manifold X has non-positive definite intersection form. And this is very important when we use the obstruction from the Heegaard Floer homology, even in gauge theory or other kind of flow theories. However, it's still not true. Like for any three manifold Y with positive first Betty number, you can define the D invariant. In order to define in a good way, we need to restrict our Y has the standard module HF infinity Y. So what does that mean? Now we have a three manifold Y. There are different versions of this Heegaard Floer homology. The standard module is defined in terms of the version of HF infinity of Y. This restricts some torsion spin C structure here. So if we can describe this module, HF infinity Y over the spin C structure as the exterior algebra of the first cohomology class of the three manifold Y, tensor this module FU inverse under the ring Z, then we say our manifold Y has the standard HF infinity. In that way, we can define the top and the bottom. The way we define the top and the bottom depends on the action of the first homology of Y on the whole chain complex. Just recall, like we can describe the chain complex HF infinity as the exterior algebra of the cohomology class. There is once we have this structure for the three manifold, there exists an action up to homotopy of the exterior algebra of the first homology of this Y, the torsion part on the chain complex. Then for this action, you can talk about which of the submodules over the whole module is the kernel of this action and which submodule is the co-kernel of this action. And this kind of nice structures of HF infinity will tell us like the kernel will consist of one FU copy with some U torsion, and the same thing for the co-kernel. So as we define for the usual D invariant for the rational homology sphere, now we are trying to define the D invariant in terms of the submodule of the kernel and the submodule corresponding to the co-kernel. So that's give us the D top and D bottom. The D bottom basically is associated to the grading of the generator of this FU part in the kernel submodule, and the D top is the grading information of the generator of this FU in the co-kernel submodules. That's what we define for the D invariant. So this is for general Y with B1 Y greater than 0. And also we need a kind of a generalization for the theorem of Oshman-Zabel, saying now Y is not a rational homology sphere, but has the standard HF infinity YS. And also we need to modify the full manifold it bounds. So this is a theorem given by Levine and Ruberman, saying like, suppose X is a full manifold, connected full manifold with non-positive definite intersection form, restricting the positive second Betty number is 0. And we assume the boundary is Y, and S is a spin C structures on Y that extends to a spin C structure on X. Then we have the following inequalities. So the bottom of this boundary Y at the spin C structure S is greater or equals to 1/4. This is the Euler characteristic. Sorry, this is the chain class. So this is the chain class for this corresponding to the spin C structure T of the four manifold X. And this is B2 minus the minor second Betty number of our four manifold X minus 1/2 of B1Y. And the top of the three manifold Y at the spin C structure S is greater or equals to 1/4. This is also the first chain class at the spin C structure T, and this is the same as the negative second Betty number, but now you have plus 1/2 of the first Betty number of Y. So this is the generalization for Urschmann-Zeppel's theorems for general boundary three manifold Y and for general four manifold which has the boundary Y. How did we apply this theorem in our setting? So in our setting, remember we have this complex curve C in CP2. So now what we are trying to do is we take the complement of the curve C inside CP2, which means that we take our four manifold X to be the complement of CP2 of the neighborhood of this curve. And now this is the four manifold of this boundary, and our boundary Y is the boundary of the neighborhood of this curve C. So in order to apply the theorem we just mentioned, we need to check the topological information for the four manifold X and for the three manifold Y satisfy the assumption or not. So we need a good description for the three manifold Y. And Y here is a neighborhood, it's a boundary of the neighborhood of the complex curve. And this complex curve, remember, it has the singular point Z1, Z2, etc., Zn, which give you the link of singularities is L1, L2, L3, Lm, and it has genus G. So here we describe our boundary Y, which is a surgery on the knot K, and this knot is coming from the connect sum of L1 hat, L2 hat, etc., Ln hat, and it connects sum of G copies of B hat. I'll just to explain the meaning of this notation. So remember, Li is the link of singularity. It could be a knot, it could be a link. And Li hat is the notification of Li. Notification of a link is meaning like you attach a band to different components over the S1 cross S2 segment. So each time you're adding a band, you actually need to add a one handle to the three manifold S3. So you actually give a new knot Li hat, not inside S3 anymore, but inside S1 cross S2. And if you have more than two components, you just need to add more bands, and then you just have a connect sum of S1 cross S2. And what is B hat? So B is the bromine ring. And a B hat means the bromine knot. The bromine knot is obtained by doing zero surgeries on any two of the component of the bromine ring. So you still get a knot, but now your knot lives inside S1, the two copies of connect sum of S1 cross S2. So it depends on your genus. If you just have genus 1, then you just consider one copies of the bromine knot. But if you have genus G, you probably need to consider the G copies of a connect sum of this bromine knot. That's what we wrote here. So this knot K consists of the notification for the link of singularity, and it consists of the G copies of this bromine knot. And now this new knot is not lives inside S3 anymore, but it lives inside some copies of S1 cross S2. And the number of the copies you need depends on the topological data of this link of singularities, right? So if you have if your curve has genus G and each Li has Ri components, then R equals to 2G plus the sum of Ri minus 1. And just there's a remark. As a three manifold S1 cross S2, no matter how many components you're doing the connect sum, this is always standard. So it has standard HF infinity module. And here Y is, so here I didn't specify the surgery coefficient for Y, but actually, if you don't care about the details too much, you can simply regard Y as large surgeries on this knot inside the connect sum of S1 cross S2. So, so this is standard fact. Like if you're doing large surgeries on a standard HF infinity three manifolds, you still get a three manifold with standard HF infinity. So here Y also has standard HF infinity structure. In that way, we can define the top and the bottom of Y at some particular spin C structure as what we defined before. So this is the topological information of Y. And what about X? Because remember in the theorem, the key thing we need X to satisfy is that the B2 plus of X equals to 0. It has non-positive definite intersection form. So here, the good thing is like in our setting, X has trivial intersection. So which means like B2 plus X and equals to B2 minus X equals to 0. So it satisfies the assumptions in our theorem. And B2X equals to R, where R is exactly what defined when we describe the topology of Y. And this is determined by the complex curve C. So applying to this theorem in our setting, we just get the two inequalities. The bottom of this Y at some torsion spin C structure S, which can extend to the whole four manifold, is greater or equals to minus R over 2. And the top of the three manifold Y at this torsion spin C structure S, which can extend to the ambient four manifold, is smaller or equals to R over 2, where this R is defined as the 2G plus the sum of Ri minus 1. However, so the last piece we need to figure out in order to prove the main theorem is the computation of the top and the bottom. So how to compute this themes? Just to recall, like the right-hand side of this inequality depends on the topological information of this curve. And the left-hand side is the D invariant, which comes from the Heegaard Floer homology. So is there an easier way to describe the D invariant or compute the D invariant of these three manifolds? Because we have a nice structures, we have a nice description for the three manifold. We describe it as the surgery along some particular knot K in this ambient three manifold. And moreover, we know it's not only a surgery, actually it's a large surgery. So there's a very convenient way to compute the D invariant of large surgeries for our knots inside S3 or even inside the connect sum of S1 cross S2, as long as we know the whole chain complex. So here, yeah, I didn't introduce what this notation means, but as we say before, if you have an oriented closed three manifold Y, you can just construct some flow chain complex CF minors over Y at some spin C structure S. So now the same is like if you have a non-homologous knot K inside the ambient three manifold Y, you can just give a filtration along this chain complex, which give you a more a bigger chain complex, which we usually call CFK minors of Y, and with the information given by the knot. So this is what this notation means. And in general, we most of the time we only consider knot K inside S3. So we have this standard notation CFK minors of S3K. However, in our setting, our manifold Y is obtained from is obtained from the surgery along this knot K inside R copies connexon of S1 cross S2. So in order to compute this D invariant, we need to compute the whole chain complex CFK minors of this connexon of S1 cross S2 with the knot K. There are several points. The first point is like, just remember all these one are the notification of Li. If Li is a knot, then this is an edge break knot. And Li hat equals to Li. We just need to understand CFK minors of S3 of Li. And because this is an edge break knot, it falls into the bigger category of L space knot. For such knot, you can just compute the whole chain complex from its Alexander polynomial. So this is pretty straightforward and easy. But if you have Li is, for example, is a two-component link, then Li hat is a knot inside the inside S1 cross S2. So we want to compute CFK minors of S1 cross S2 and Li hat. There's a joint work of Mache and Yin. We prove like this whole chain complex is homotopy equivalent to CFL minors for this link inside the S3, not inside S1 cross S2, which means like if you know the Heegaard diagram for this link inside S3, you can recover the chain complex of this notification, and also you can recover the H1 action. Here, H1 action means the first homology of the ambient 3 manifold acts on the chain complex. So we use this way to compute, for example, compute the case when Li equals to T22 or even T22N tors link. They're both two components link. The last piece we need is the B hat. We also need to know we also need to understand the CFK minors of connexon of S1 cross S2. Maybe two copies of connexon with two copies of connexon of S1 cross S2 and the bromine knot. So this has computed in this has been computed by Oshvan-Zabel before. It is a very known result, and you know it's H1 action, and you know which one is the kernel, which one is the co-kernel, and we have a very good understanding for this one. Yeah, that's basically how we prove our main theorem. After we understand each piece, we just need to tensor the chain complex together. So if this is just a knot, and we tensor some S2 cross S1, there's the notification, and then we tensor CFK minors of some copies of S1 cross S2, and this the bromine knot. So this is how we compute the whole chain complex, CFK minors of several copies of S1 cross S2 with the knot K. How does that relate to our questions of double points? So if the curve C has positive or negative double points, the link singularities at that singular point correspond to positive or negative half link. As we say before, we actually compute the whole chain complex for T22N tors link very explicitly. We find T22N, we find this chain complex T22N at S3 or the notification for this link inside S1 cross S2 is written as the direct sum of two subcomplex. Each subcomplex has a very standard staircase. If you're familiar with this picture, the standard staircase is really just the chain complex for T22N plus 1. So this is a torus knot. It has n staircase, and you have the direct sum, and the other one is T22N minus 1, which is also the staircase, but this n minus 1 steps. So this is the whole chain complex for T22N. The H1 action you can recover is like it sends the subcomplex corresponding T22N plus 1 goes to the complex corresponding T2 to a -1, which is very straightforward. So you know the D top and D bottom very easily. And for negative double points, we need to consider the mirror of the Hopf link or the negative Hopf link. So we generally also compute the mirror, the chain complex of the mirror of the torus link T2 to N. And we find that the complex also just consists of two subcomplex. You just write it as a direct sum of the two complex. Each subcomplex corresponding to the staircase of the mirror of the torus knot T2 to N plus 1, T2 to N minus 1. And the H1 action sends the shorter staircase to the longer staircase. And also in that way, you can compute the D top and D bottom. And that's how we prove our main theorem. Thank you very much for everyone's attention. And yeah, thanks.